Okay, so what we're going to do now is we're going to do 2.1D, the supplemental video. Um, in this video, we're focusing on the first half of key question 2. So what you saw in part 1 of 2.1D are the different types of Ks. There's Ka, which is the ionization of acid, Kb, ionization of base, and Kw, which is the autoionization of water, and KSP, which is the ionization of a salt. So all of these K are equilibrium constants that are used to sort of help us determine like how much of the acid, base, or salt ionizes. Now, we noticed that here that there are some trends that the higher the Ka and higher the Kb, the stronger the acid or base respectively. And we mentioned for salts, the higher the Kp, the more soluble the salt, but that depends on the ionization product. So let's talk about that. So here for this side, we have KSP does not always mean more soluble. And with weak acids and amines, it's very easy to predict which one's in stronger by inspecting the Ka and Kb. So again, the greater the Ka and Kb's, we know this is going to be the stronger the acid or base. And that's because HA is a one-to-one compound, meaning that if you have a weak acid, given the general formula HA, and you break it apart into its proton and the anion, you'll see that there's always, if there's 1 mole of this, there will always be 1 mole of H+. However, with salts, this comparison is not so straightforward. So it's only straightforward if you have similar substances. So what do I mean by that? Let's say you're comparing BF2 and Ag2S, you're comparing their ionizations. We can see that in both cases, when they break apart into 3 separate pieces. So you can sort of compare them from there because they have 3 separate pieces. Or if you're looking at the same type of salt, like if you were wanting to compare silver sulfide with silver chloride and you're focusing on the silvers, then that may work as well, depending on what you're looking at. But we can't always just look at the KSP. So another thing we can look at is molar solubility. And we can utilize that in order to figure out which one is more soluble. The higher the molar solubility, the more soluble substance is. So what is molar solubility? It is the number of moles of a substance that can be dissolved per liter of solution before the solution becomes saturated. And let's look at an example of how we do that. Let's take something like BaF2, and we're breaking it apart into its ions, Ba2 and 2F-. Now remember, the KSP is going to be the concentration of the products over the reactants, but since this reactant is a solid phase, we don't include it in the KSP value. So it's just going to be the concentration of the products. And of course, we raise the concentrations to the powers of their coefficients. Okay, so now let's look at the concentration of each of these species. We're going to use this information to calculate the molar solubility. First thing we're going to do is we're going to set these values to X based on our starting species. BAF2 is sort of going to be our X. We have one of these. So anything that also has a 1 as its coefficient will also be X. Anything that doesn't will have a 2X. So if we look in the balanced chemical equation, Ba2 plus has a coefficient of 1, so concentration of Ba2 plus is going to be X. Whereas for fluoride, it has a coefficient of 2, so that's going to be 2X. Okay, now that we have that down, the next thing we're going to do is we're going to plug that into our KSP expression. Our KSP is concentration of Va divided by the times concentration of F minus squared. And so we go ahead and plug in our X and our 2X, and we square that 2X. And that gives us X times 4X squared, and when we multiply that out, we get 4X cubed. Once we have that, we can go ahead and set this equal to KSP. Now the KSP is a constant that you will either be given this number or you could look it up in a chart. You don't have to memorize any of the KSP values. So they'll give you this number. And so we set our KSP to whatever value we're given. So we're given the KSP of barium fluoride is 1.84 times 10 to the minus 7, and that's equal to our 4X cubed. Once we have that information, we can then go ahead and solve for X, and our X is going to be our molar solubility. So how do we get X? Simply, we would utilize our reverse order of operations since we were trying to isolate our unknown there. So we would start by dividing both sides by 4. Once we have that, we would then take the cube root of what we get from that. And that's what our x is going to be. And if you do that math out, you get the x to be 0.00358 molar. So this value right here is the molar solubility for barium fluoride. And again, the higher the molar solubility, the more soluble a substance. So sometimes it's important, we can't just look at the KSPs. We also have to look at the molar solubility to sort of help us determine which one's more or less soluble. Okay, so on this slide, we have just a bunch of examples if you sort of want to see what this sort of thing looks like for different type of species. And this sort of thing may be helpful to just sort of take a look. So what I would recommend that you do I would recommend that you cover up this portion here. So wherever it's written in black, you sort of cover that part up and see if you can solve it on your own. See if you can write down the expression to solve for the molar solubilities of each. So all of these answers here are molar solubilities for the salt. Okay, there's some additional videos if you want more practice on this. This is something that could appear up on an AP exam. It's a useful thing to know. All right, now we're going to look at how do we sort of like quantify the amounts for strong acids and strong base. And we measure acid and base strengths by pH and pOH. So remember, the stronger the acid, the lower the pH, and the stronger the base, the lower the pOH. Okay, so let's say we have a problem like this where we actually determine the pH of a 0.5 molar H2SO3 solution. And again, this will help us determine how acidic it is. pH is equal to the negative log of concentration of H+. So we need to get the concentration of H+. So to help us out, we're going to write down the ionization, and this is the ionization of H2SO3. Once we have our ionization reaction, we're going to set up what's called an ICE table. So ICE stands for initial, change, and equilibrium. So what information goes here? Notice how in each column is, above each column is a reactant or a product. Let's start off with H2SO3. The initial concentration that we have, they tell us is 0.5 molar solution. That's our initial concentration. So we go ahead and put that underneath H2SO3 as our initial concentration. Now at the very start, right when the H2SO3 hits the water and becomes aqueous, we have no product yet. So here we are just going to have 0. Now once it starts to ionize, what's going to happen is we're going to lose some H2SO3. So the amount we lose, we're not really sure, but we're going to put minus X to show that we're losing some of it. And what's going to happen to the concentration of H+ and HSO3 minus? We're going to increase those. So instead of putting a minus X, we're going to put a plus X. Once again, we don't know how much we are going to make, but we know we're going to make some of it. Okay. So now let's look at our equilibrium concentrations, because this is going to help us to write our K expression. Since this is a weak acid, most of this is going to stay as H2SO3. So we can say when we combine 0.5 minus X, instead of writing 0.5 minus X, we can say it's approximately just a 0.5 molar. And that's again because X is going to be really small compared to 0.5. So we can make that approximation. Here for concentration of H+ and HSO3, we're going to just add X. So 0 plus X and 0 plus X gives us X and X. And so these are the equilibrium concentrations for all of our species. And the cool thing is once we have that, we can utilize that and plug it into our Ka. So remember, Ka is concentration of products of reactants. And for this equation, this is what it looks like. And you would be given the Ka value, because remember this is a constant. So the value for the Ka of H2SO3 is 1.54 times 10 to the minus 4. All right, so once we have that, we can go ahead and plug in all of these values here, and we can use that to solve for X. Once we solve for X, that's going to give us the concentration of H+. And once we have the concentration of H+, we can plug it in for our log, for our pH expression. Okay, so here we have x times x over 0.5. And again, all I did was I just plugged this information into the equation. So underneath the H2SO3, we have 0.5 molar concentration that goes here. And underneath H plus and HSO3, we have x and x, so that goes there. Now, once we do that, we can go ahead and solve for x. So we would cross multiply 0.5 times 1.54 times 10 to the minus 4. And that will equal to x squared. And then we go ahead and use that to solve for our x. When we do that, we find that x is equal to 0.00877 molar. So when we solve for x here, we get this value. And then we can go ahead and plug that into the pH expression. Once we have that pH is equal to 2.1. So we sort of use this to figure out the pH. All right. So for bases, we can do this same thing depending on what type of base we have. For bases, if it's a MOH base, so a metal hydroxide base, we sort of do the same thing that we did for KSP. So let me just go back where we can use the molar solubilities to determine how much of the base dissolved. And if it's a base like NH3, an amine base, we would do what we did here for the Ka. So that's how we would do it for bases. Once you have the concentrations of OH minus, you would use that to get the POH for your base, and that's the sort of thing that you would do to solve. Here's some additional videos that you can watch if it's helpful for you to sort of just get a sense of how to do these problems. In the next class, we are going to tackle some practice problems like this. All right, hope you found this video helpful. Have a quality day.